This is a demo of PlasMaSim, which is a simulator for the PlasMa machine. Now the machine itself is a simulator of a mini or mainframe computer system, so maybe this is a simulator squared. Either way, it's a means of exploring the potential of a machine before deciding whether to build one. It can also be used to develop and test programs, although doing everything on the simulator misses out on the hands-on challenge and the fun, which was the reason for building the machine in the first place. And the simulator was designed to develop and verify the firmware running inside the real machine, so most of it uses exactly the same code. The differences are mainly in the routines which drive the hardware chips for the lights and switches, and these are replaced with operating system calls to control the screen and QWERTY keyboard. And the program is available for 3 different platforms: Microsoft Windows, Mac OS and Linux. It runs in a command window, sometimes called a terminal window, and is driven solely by the QWERTY keyboard. Now, the user interface seems crude at first compared to a traditional Windows program driven with a mouse or touchscreen, but it's sufficient to operate all the functions available on the real machine. And once you become familiar with the commands, it can be even quicker to drive. So how do you drive it? Well, there are 3 types of switches to control the real machine. There are momentary ones, such as run, step, reset. Then there are latching switches for load values, breakpoint values, and memory addresses. And lastly, there's the 16-button keypad. And the momentary switches are simulated by single key presses on the QWERTY keyboard. So for example, run is R, step is S. Now they don't all have the same first letter, unfortunately. For example, reset is Z and stop is Q. But they are all shown in the help section at the bottom part of the screen. There's R for run, Z for reset. We'll see more in a minute when we load a microcode. The latching switches and the keypad are simulated by pressing the keys 0 to 9, that's this numeric row along the top, and the lowercase letters A to F, and these represent the 16 possible hex digits for a nibble. This means you can set the latching switches 1 nibble at a time, which is a lot quicker than setting 1 bit at a time on the real machine. You have to select which row of switches you want by pressing the up-down cursor keys, and the current nibble is highlighted with brackets. You can see it's currently on the load switch row, these square brackets here in red. We can go up to the keypad area, or down to the break row, or down to the memory address switches. And you can move the highlight right or left using the arrow keys again, or backspace also goes left. And as you enter hex numbers 0 to 9 and A to F, the highlight moves to the right automatically. So for example, to set hex 1, 2, 3, 4, 5, 6, 7, 8 onto the break switches, we'll press the down key to get to the break switch. We're on the leftmost nibble and we just press 1, 2, 3, 4, 5, 6, 7, 8. And the graphic symbols show the physical state of the switch, up or down, and the value is confirmed on the right in hex and decimal. And the keypad operates the same way. Move the cursor upwards. We're on the keypad area here. Only a single digit is available as it represents a single button press. The keypad is only functional when a program reads it. And that's all you need for the basics. So let's do a test run. I've just loaded the simulator, so it's effectively the same as the machine powering on. And as with the real machine, you have to load a microcode first, otherwise it won't know how to interpret instructions. The 3 microcode lights here are a binary representation of the microcode number, and it currently says 0, so no microcode is loaded. So, as we saw before in the other videos, we set the microcode number on the most significant nibble of the load switches. So move the highlight there, press 1. We need to set FMP force microcode load. And down here the little m sets it and a big M resets it. So I'll do little m, and the FMP light comes on here. We need to reset the registers. Specifically we need to reset PC, but reset them all with the Z key. And then we just press R to run. And the microcode's loaded, the halt lights come on, and we just need to reset the FMP flag with Shift and M, and we're ready to go. We've got the full set of commands available now at the bottom, because the machine can do a lot more now with the microcode loaded. The title along here, which has the version number of the simulator, spells out which microcode you've got. In this case, microcode 1 is toy A. So let's enter a similar program to before, which adds a register to itself, so we double its value each time round a loop. So we need to confirm PC is 0. This is PC along here. We'll press the Z button. That's where we're going to load the program. And we need to confirm the target load light, which is this red light here, is set to the instruction register, which it is by default. And you can move this up and down with the page up and page down keys. Okay, we'll start with an instruction to load a value of 1 into register 3. So we make sure the highlight is at the correct position on the load switches. We need the least significant 4 nibbles, as all toy A instructions are 16 bits long. Then we just enter the instruction. 7 for the opcode, 3 for the target register, 0, 1 for the 8-bit value. And then we press uppercase L to load and increment. And the commands are case sensitive, as you've realized. So lowercase l is load down here, and uppercase L, which is only applicable to the IR register, loads IR and increments PC. Right, we'll enter the next instruction to add register 3 to register 3 and put the result back into register 3. One for the opcode, 3 for the target register, 3 for the 2 source registers to be added. Load and increment. And the next instruction is a jump back to address 1. C for the opcode, 0 for the condition register, 0, 1 for the target address. Load. Now we confirm the program is correct using the incdecpc command, which are these square brackets here. So PC is 0 and the instruction is the 7301, and you get a nice mnemonic of the instruction. Load, it says load address, but that's load register 3 with the value 0, 1. Go to the next PC, and it's an add register 3 with register 3 and put the result back into register 3. Next one, jump, which means put a 1 into PC. Okay, that looks perfectly fine. We'll go back to PC 0 and we'll start the program. I'll run it in single step mode just to see what happens. And you just press S. And you can see the first instruction has been obeyed and register 3 now contains a 1. The next instruction to be obeyed will be an add. Add it to itself. Press S. And the value is now 2. You also get a hex and decimal representation of the register alongside each one. So we'll do a few more steps. And you can see the value doubling each time. And as we saw before, it eventually overflows and goes to 0 and stays at 0. Right, let's reset PC and run this at full speed. 0, run. Okay, that's too quick to see what happened with the registers because it's overflowed so quickly. So we'll stop, Q, 0 the registers, and we'll run at a medium speed, U. There we are, that's a bit better now. I'll do that again. Stop, 0, U. And just a good measure, we'll do it at slow speed, 0, N. There you can see what's happening now. Now the three letters R, U, N for run are the three speeds. We've got full speed, medium speed and slow speed. Q to stop. Okay, let's try the teletype. We'll replace the jump instruction with an IO instruction to write the value of register 3 to the teletype. So we set PC to address 2, confirm this is the old jump instruction, and we'll overwrite this with an instruction to write register 3 to the teletype. So we position the highlight on the load registers. We want 9 for the opcode, 3 for the source register, FF for the special IO memory address, and then load and ink. And now we need to enter the new jump instruction, C001, and load. Right, we reset and we'll run. And you see the values appearing on the screen, but as expected the register overflowed too quickly to see anything, so I'll stop, I'll reset, and we'll run at medium speed. And you can see the values clocking up there. I can stop it there, and you can confirm that the values do in fact double each time until we get to the maximum value we can store, and the next double overflows and we go to 0. Okay, the final test is the keypad. I'll use the same program as in the last video. We'll set PC to 0. We'll enter an IO instruction to read from the keypad. So that's 8, 3, FF. So we're going to read into register 3. Load an increment. And now we need an instruction to write that register to the teletype. So it's 9, 3, FF. Load. And the jump back to 0. C000. Load. Just confirm. Here's address 0. We've got a load memory FF into register 3. The next one, store register 3 into memory FF. And the next one is jump back to 0. So reset and run. Okay, well, as we expected, the keypad light has come on. So the program is waiting for data from the keypad. So to enter values, we need to move the highlight up to the keypad area. So up arrow. And then we can press buttons or simulate pressing buttons. We'll do 1, 2, 3, 4. And if you noticed, register 3, those numbers were shifted in from the right hand side as we saw on the machine. If we're happy that was what we meant to type in, we can press run. The value comes out on the teletype, 1, 2, 3, 4, and the keypad light is back on again, waiting for the next number. And as before, if you make a mistake with the numbers, let's type in 1, 2, 3, 3, when we should have said 1, 2, 3, 4. That's the state of the register, 1, 2, 3, 3. So you just carry on typing. We'll do 1, 2, 3, 4. And you can see all the bad numbers were shifted out and the correct numbers are shifted in. We're happy with that, so press run, and there's the other 1, 2, 3, 4 there. So we can do A, B, C, D. There's the value. Run, and it comes out on the teletype. Okay, so that's about it for the simulator. The program itself and the user manual for this Toy emulation are downloadable from the Philisound website, and the instruction set is in a separate document, so you'll need that as well. Okay, thanks for watching.